Okay, so in this slide, we're going to practice the skills that you learned not only in drawing Lewis dot structures, but the information about how to use that Lewis dot structure to determine its VSEPR notation or its AXE notation, which is linked to a particular shape or geometry of that molecule. So when going through these three examples or doing any problem where I ask for the Lewis dot structure and its VSEPR notation and shape, I recommend you have your periodic table in front of you, as well as the rules for drawing Lewis dot structures, and this table from the previous slideshow that links VSEPR notation with molecular geometry. So I recommend you have those in front of you when doing these kinds of problems. So to do these three examples, I asked for determining the molecular geometry of each, but the first thing you always got to do before finding the geometry is you need to know the Lewis dot structure, because it's the Lewis dot structure that will help you determine the VSEPR notation, and the VSEPR notation will help you determine the molecular geometry. So first thing we're going to do is for CFCl3, we need to draw its Lewis dot structure. So we need to figure out how many valence electrons that molecule CFCl3 has. So carbon's in group 4, so it contributes 4. Both fluorine and chlorine are in a group 7. And so when summing those up, you get 32 valence electrons. So 32 valence electrons for CFCl3. That's the first step for drawing the Lewis dot structure. Then I have to do my central atom, which in this case is the first atom, carbon. The first atom will always be the central atom unless it's hydrogen. So carbon's my central atom. I'm going to scatter my outer atoms around the central atom. In this case, the F and the Cl. It doesn't matter where you scatter them as long as they are around the central atom and that there's 3 chlorines and 1 fluorine. Now we're going to go ahead and draw, distribute our 32 valence electrons by first single bonds from the center atom to the outer atom. Remembering that single bonds are 2 electrons. So 2, 4, 6, 8. I have now used 8 of my 32 valence electrons. I continue to use the remaining valence electrons to complete the octet on my outer atoms. So I'll just start with this chlorine first. So 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So I have used all 32 of my valence electrons. All of my outer atoms are happy, meaning they have an octet. They are surrounded by 8 valence electrons. Remembering electrons in the center are shared by both. So this chlorine has 1, 2, 3, 4, 5, 6, 7, 8 electrons. Same for these 2 chlorines and this fluorine. My central carbon atom has 2, 4, 6, 8 valence electrons. So all my atoms are happy. So now I've got my Lewis dot structure. Now I can go on to determine the VSEPR notation using that AXE format. A being the central atom, in this case carbon. X denoting number of bonded atoms attached to the central atom. At this point, it doesn't matter that these atoms are different. I just need to know how many are attached to the central atom. I've got 1, 2, 3, 4 bonded atoms. I have no lone pairs of electrons on my central atom. I only care about lone pairs on the central atom for VSEPR notation. So my VSEPR notation, A being the carbon, X being the 4 outer atoms, and there's 4 of them, is AX4. And looking at table 10.1, you will see that anything with an AX4 molecular geometry or VSEPR notation has a tetrahedral molecular geometry. So that's the answer for CFCl3. Let's go ahead and do BH3. Some are valence electrons. 3 from boron, 1 from hydrogen, multiply by 3, I have 6. Boron's going to be my central atom. Scatter my outer atoms, scatter my outer atoms around it. My 3 hydrogens. Now I'm going to go ahead and distribute my valence electrons by first single bonds from the outer atom to the inner atom. So I'm going to just go ahead and do this. So let's just say that's one bond. I have to try and find my eraser here. I don't know if I can get an eraser. Oh, I can. Perfect. Perfect. See, learning new things every day. So I'm going to do my single bonds from my center atom to my outer atoms, counting valence electrons. So 2, 4, 6. I have now used all 6 of my valence electrons. My hydrogens are happy. They have a duet. And you may say, well, wait a minute, boron's only got 2, 4, 6 electrons. That's okay. That's okay. Boron can be happy with less than an octet. How do you know that? We're not going to talk about the reasons why that is, but just know that it's okay for boron to have less than an octet. So this would be the appropriate Lewis dot structure for BH3. Okay, you wouldn't want to be adding extra electrons because you don't have them to add, so this is correct. Looking at this structure, for my VSEPR notation, I have my central atom, which is boron. I have my 3 atoms that are attached. So my VSEPR notation would be AX3. And if you look at table 10.1, the associated geometry with that is trigonal planar. Last but not least, we have SeO2. We need to determine its molecular geometry. But first, we got to find its Lewis dot structure. So, it's starting to get to be a habit, right? Find the number of valence electrons for that molecule. They're both in group 6. So you do that sum, 18 valence electrons. My central atom is going to be the selenium. Scatter my other 2 atoms, my other atoms around. Start doing single bonds from my center atom to my outer atom to start using my valence electrons. So 2, 4. I have used 4 of my 18 valence electrons. I'm going to continue by completing octets on my outer atoms. So 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I have now used 16 of my 18 valence electrons. Both oxygens are happy, meaning both of those oxygens have an octet of electrons. They are surrounded by 8 valence electrons. I still have 2 more electrons that I need to place. Any extra electrons, to place, always go in the center atom. So 17, 18. So I have now placed all 18 of my valence electrons. But selenium still isn't happy. Does selenium have an octet of atoms? No, it only has 2, 4, 6. Do either of these oxygens have a lone pair that would be willing to share? And the answer is yes. You could either have this oxygen on the left donate or share a lone pair with selenium to give you a Lewis dot structure where you have a double bond on the left side of the structure. But hopefully you could also see that aside from this oxygen on the left donating a lone pair, you could have also had an oxygen on the right donate a lone pair. I'm not going to go ahead and draw that Lewis dot structure because either of them would be correct, but This is the one I'm going to refer to here because that would be a correct Lewis dot structure for, whoops, as long as I have it be SE, right? That would be a correct Lewis dot structure for SeO2. This one up here is not correct because as it is written, selenium doesn't have an octet. But looking at this Lewis dot structure for Se2, you can go ahead and write down what the VSEPR notation is for that molecule, that AXE notation. I've got my center atom, selenium. I have two outer atoms, so that would be AX2. But I also have a lone pair of electrons here, which I need to take into account. So my VSEPR notation for this molecule is AX2E, this E referring to the lone pair of electrons on the central atom. And looking at table 10.1, anything with an AX2E VSEPR notation has a molecular geometry that is bent. I believe your lab manual may also call it angular. Both I would accept. Okay? So that is how you use Lewis dot structure in conjunction with this AXE notation to say something about the shape or the geometry of small molecules.